All right, welcome and thanks for joining. Today what we're going to be talking about is the binomial theorem. So just talking about a binomial in general, a binomial is a polynomial with two terms. And that's not anything that's really new to us. We're used to working with a lot of binomials, trinomials. So what we're going to use to give an example is the binomial x plus y. The binomial theorem allows us to expand x plus y to the power of n. And that's beneficial and time saving, because if we were doing something like x plus y squared, we all know how to do that. That's just like your classic case of quote unquote FOIL. But if we had something like x plus y to the 10th power to the 30th power, it would become way more in terms of distributing. So before we go through all of 8.5, I just want to give a prior warning that it is sort of writing intensive, but it is less writing intensive than actually multiplying all of this out. So just to walk us through three that we already know, x plus y to the 0 power, that's going to give us 1. Remember, the reason there is because anything to the 0 power will give us 1. So notice what we get as a result is one term. X plus y to the first power just gives us x plus y. So notice here now we have two terms. X plus y squared, our classic case, the thing that we're really used to, that's going to give us x squared plus 2xy plus y squared. So notice now I have three terms. So the sort of really cool thing with binomial expansion and the binomial theorem is the fact that it's not just about looking for a pattern or the pattern. Binomial expansion, there's patterns that are going on with so many things all at once. So there's a lot that you can grasp from just simply an exponent or a coefficient. So the first thing that we could talk about right away is looking at this binomial expansion. So we had x plus y to the 0, to the first, or to the second. And the number of terms that you're getting is always one more than the degree. So when my degree was 0, I got one term. When my degree was 1, I got two terms. When it was 2, I got three terms. Continuing this a little bit, if I had x plus y to the third power, what I'm going to get here is x cubed plus 3x squared y plus 3xy squared plus y cubed. Here, there are four terms. Again, our degree was 3, which gave us 4 terms. Now, when our degree is 4, we can right away, sort of be thinking, okay, I'm going to have 5 terms, and I'm going to have 6 terms. So, hopefully we can sort of get that process down. Some other cool things happen. If you look at this first term, it's always the lead term to the degree. So it's x to the third. The last term is always y to the third. So here I know I'm going to have x to the fourth. We'll talk about how we get these coefficients. That's sort of a cool thing as well. But we're going to have x to the fourth plus 4 x cubed y plus 6 x squared y squared plus 4 xy cubed plus y to the fourth. Another thing to notice, and again, this is all stuff that we'll still talk about a lot, but if you look at each individual term, so here, the exponent is 4. At this term, the exponent is 3 and 1, so it's a total of 4. Here, it's 2 and 2, so a total of 4. Here it's 1 and 3, which is a total of 4, and here it's 4, which is, a total of 4. So all of the individual terms have a degree that is equal to the degree of your binomial. All right, let's continue on. So now we have x to the fifth plus, I'll tell you right away, it's a 5 here. Oh my gosh, look, another thing that you can notice. Yeah, the degree is always equal to that second coefficient. Again, that's something that we'll talk about because sometimes that can change in a sort of different way. Uh, but knowing that this is going to be a 5 because of this 5 is a helpful thing. And then, we could look at something else. What's going on with our x's is that it's constantly decreasing by 1. So here we had x cubed, x squared, x, no x. And on the other hand, our y's are doing the opposite. They're increasing. No y's, 1y, 2y, 3y's. So now I had x to the 5th, so this will be x to the 4th. But I have to have a y here because the sum of these exponents has to be 5. Plus 10 x cubed y squared plus 10 x squared y cubed plus 5 xy to the 4th plus y to the 5th. Hope you left enough room, because I did. All right, looking at how this changes now. So if we put a coefficient in front of this 2, that's going to change our binomial expansion. This is what we're going to deal more commonly with, is when there's something more than just 1x and 1y. Sort of boring. So 2x plus y to the 0 power, anything to the 0 power is 1. 2x plus y to the first is going to give me 2x plus y. 2x plus y squared, I wouldn't expect you to do binomial expansion or binomial theorem on this. I think you should just, regularly FOIL. You know how to do it. So this would give me 4x squared plus 4xy plus y squared. So when we have something like 2x plus y cubed, now I know you're thinking like, oh, I could just multiply this whole trinomial by 2x plus y. Wouldn't that be shorter? And in some cases, maybe. But it's not how we're going to do it, because it's about getting the process down so that if this was something like 90, you could skip all that work. So this is where we're going to use the binomial theorem. And again, the binomial theorem is really just a whole bunch of patterns, just tons of patterns that are all happening at one time. So initially, what we're going to just talk about right away is the coefficients. I've talked a little bit about the exponents already anyways, but the coefficients, the lead numbers, they follow a pattern that's called Pascal's triangle. And in the next slide, we'll write out that whole Pascal's triangle. Well, not the whole thing, but you'll get the process down. They're also always in the form of, and this is red, n choose r. It can also be written as n over r in these parentheses. And what that really is, like the way that that is calculated, is n factorial over n minus r factorial, r factorial. So this is how all of the coefficients in Pascal's triangle are found, which means when we go and we write out Pascal's triangle, if you don't necessarily memorize what's in like the 5th position of the 10th row, you can always use this, and a lot of people will use this to get those coefficients. And again, what this means, so n choose r, that means if you have n terms in how many ways can you choose r of them? So sort of going to tie into the rest of the chapter as well. N choose r just means if I have n, some number of terms, in how many ways can I choose r of those terms? And again, this is the formula for doing that. So what we want to talk about next is actual Pascal's triangle. So if we go to our next slide, it's sort of a blank slide, not very interesting there. We should have an apostrophe on Pascal's. So Pascal's triangle. At the top of the triangle, you have 1. Ooh, fun. And then on your next row, you're going to have 1 and 1. Again, what this is giving you is the coefficients as I binomially expand. Then I'll have 1, and what you're really doing is adding these two things together to get what's in the middle of them. So I'm going to have 2, 1. Then I'll have 1. These outsides are always going to be 1. Again, I'm still adding the 2 things above it to get what's next. So 1 plus 2 is 3. 2 plus 1 is 3. You'll end up seeing this symmetry hold throughout. I'm going to have 1 and 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. But we'll continue going, but just to add something else to this. Now, this right here, 1, this is when you have a 0 degree. Remember, when we had x plus y to the 0 power, we just got 1. When we had x plus y to the first power, our coefficients ended up being 1x plus 1y. When we had x plus y to the second power, we ended up having 1x squared plus 2xy plus 1y squared, our classic case of FOIL. If we have something to the third degree, we have 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. So this is what's really helping us find all those coefficients, not necessarily the exponents, but the coefficients of the binomial expansion. We'll continue this on for a couple more. So we'd have 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, 1, 7, 21, 35, 35, 21, 7, 1, and we'll do one more. 1, 8, 28, 56, 70, 56, 28, 8, 1. Now again, you do not have to memorize all of this. A lot of it you really should, like this 8th row, are you going to remember that? Probably not. That's fine. You should know this like top half of this pyramid. I'd say that will be stuff that will be very frequent. But something to keep in mind is that if you're looking for any position, once we talk about how to do n choose r, we'll talk about that sort of in the examples. But n choose r is what's going to allow us to get right away any of these coefficients. So you won't necessarily need to memorize them. All right, we're going to skip that next slide. We'll talk about that in the examples. And we'll go to binomial expansion. So this is going to be talking about both the coefficients and the exponents. So if I have x plus y to some power n, my lead term is always going to be x to the power of n. Remember that it always has a sort of coefficient of 1 here. So it's just x to the power of n. Then I have n, whatever the degree is. I sort of brought that up when we were doing a couple of those. So if this was degree 5, I'd have 5x to the power of n minus 1 times y. So whatever my lead term was, again, if I said 5, this is x to the 5th, this will be x to the 4th. What's going to happen here is I'm going to leave a little bit of space. It's going to keep decreasing. So now it would be x to the 3rd, and so on and so forth. What comes here, so this is part of that Pascal's triangle. So this is where we'd be doing n choose 2. The reason this is 2 is because your r value is 2. R, you're going to be looking at whatever's right here. I mean, we're going to write that right here as well. But when this says n choose 2, the reason it's 2 is because that is the exponent on the y. So your sort of formula for any of these, what I'm putting in right here, is that you're doing n choose r times x to the n minus r, y to the r. So when we talk about what r is going to represent the exponent of the second term. n represents the degree of the binomial. Here we're going to have n x y to the n minus 1. Notice the symmetry here. All that changed was the x and the y's exponents, and then y to the power of n. An infinite number of things could happen in between these. An infinite number of things can happen between these. So the following binomial expansions of 5x plus y to the third power. The way that we sort of use binomial expansion. Okay, so it's to the third power. I'm doing a little bit of the examples, I know. So that means there's going to be 4 terms. The first term has to have a 1. The last term has to have a 1. The second term is always starting with that degree. So 3. So this must be 3 because it's symmetric. Then the x right here is going to be x to the third, and it decreases x to the second, x to the first, and no x. The y's increase, no y, y to the first, y to the second, y to the third. So your whole expansion of this is just x cubed plus 3x squared y plus 3xy squared plus y cubed. What I did up here, I know that seems like an easy one, but what I did up here is like the type of work we'll be showing. So you could just imagine if there are like 7 terms or 6 terms, we're going to be showing a lot of work. I assure you it is not difficult work. It's tedious work, and it is significantly less tedious than actually multiplying this out a whole bunch of times. All right, we'll do one more. X plus y to the 5th power. So I know I'm going to have 6 terms. That second term is the same as the degree, so 1, 5. What's going to come next if I go back to Pascal's triangle is 10, then 10, then 5, then 1. Again, already taking up a lot of space. Looking at the x terms, so x, I know I'll have x to the 5th, and then it will decrease 1. X to the 4th, x to the 3rd, x to the 2nd, and x. And the y's will increase 1. 0 y's, y, y squared, y cubed, y to the 4th, and y to the 5th. You are going to have to be very organized with these, so I get x to the 5th plus 5x to the 4th y plus 10x cubed y squared plus 10x squared y cubed plus 5xy to the 4th plus y to the 5th. All right, that's all we're doing for the notes today. I really would recommend that we go and we watch those examples. Binomial expansion is a very tedious process, very, again, easy process, but a tedious process. So it could be very helpful to you to sort of listen to those examples and see me go through them more and more times. Otherwise, just make sure that you're following along when we go over them in class.